Okay, so hello and welcome back. So in this video we will talk a little bit about power distribution in series circuits. So basically power distribution in series circuits. So the power distribution in series circuits it's probably something you've never thought about, but it's actually something important and of course something practical. Meaning that, for example, suppose that first of all, the power in a circuit, you can calculate it in a few different ways, meaning that primarily power is equal to voltage times current, right? So voltage times current is, so yeah, we have primarily three formulas for power. One of them is P is equal to V times I, voltage times current in a circuit, or for any basically let's say that you have a resistor over here, and this resistor is connected to a power supply, and the power dissipation in this circuit is, if this is V of S and this is R, then based on V of S and R, some current is going through this circuit, and basically the power dissipation in this circuit would be V of S times I. So that way you can calculate this, and the power of course is dissipated in this resistor, which means that you can call this power the power dissipated by this resistor, or the power supplied by this power supply. That both would be the same thing, of course, same values, of course, right? So that is basically one thing that you need to know about power. Second thing is that, of course, since you know that V based on the Ohm's law, V is equal to I times R, then instead of V over here, you can write P is equal to I times R times I, which is equal to I squared R. So P is equal to I squared R. If you have basically the current and the resistance in a circuit, you don't have to worry about the voltage. You can square the current and multiply it by the resistance, and then that way you can calculate power as well, which is basically the same formula. Or since you know that basically I in this formula is V divided by R, in the same formula you can write P is equal to V times basically I, which is V to R, and that would be V squared to R. Meaning that P is equal to V squared to R is another way that you can calculate power. If in a circuit you have the voltage and you have the resistance, then you can square the voltage divided by the resistance, and that gives you the power dissipation in that circuit. So you have these three formulas to use in a circuit. P is equal to VI, P is equal to basically I squared times R, P is equal to I squared times R, and P is equal to V squared by R, right? So in both of these, R is there. In this one, you have to square the current and multiply it by the resistance. In this one, you have to square the voltage and divide it by the resistance. So these are the three different ways that you can calculate current in a circuit. Now that is one thing. And of course, power is the rate at which energy is basically consumed. Of course, energy cannot be consumed per se, but the you could say that the rate at which energy is changed from one form to another. That's more scientific, right? Meaning that power is not energy itself, it's the rate at which basically energy is converted from one form to another. For example, in a circuit like this, for example, depending on your V of S and depending on your R, you can calculate some P is equal to VI, for example, some power, you can calculate the power as, for example, 4 watts, for example. So this 4 watts, now I'm not really familiar with the units here exactly, but this is energy per unit time. This is joule per second or something like that. I don't know. We will have to talk about that sometime later, or hopefully somewhere in physics we will talk about that. But I mean, long story short, you should basically be able to distinguish between power and energy, and the units of basically then energy in electricity are different from the units of energy in physics. So that's it's a little bit we should talk about that in physics basically. But long story short, again, power is the rate at which energy is changed from one form to another. For example, here you have electrical or chemical, basically chemical energy stored in your battery, and that chemical energy is being converted into heat in your resistor. So energy is basically being converted from one form to another. Now the rate at which this energy is being converted from chemical energy into heat or heat energy, that rate, meaning that how fast it is happening, or what is the basically how fast it is happening, of course, which would be some value with respect to time, that would be basically power in that circuit. Okay. And electrical, I mean, those who deal with electronics, they usually, for example, I have a intuitive understanding of power based on, for example, when I put my hand on a resistor and touch the resistor and sense the temperature of the resistor, I can tell that, for example, based on the voltage and based on the current and based on that heat, I can tell that, for example, this circuit is dissipating so much power and so on and so forth. So, which is, of course, again, if you think about it, in electrical engineers or at least people who deal with electronics, when you say power is being dissipated, it's actually not the scientific way of talking about that, because power is not really being dissipated. Power is just basically the rate of change of energy with respect to time. So, or the rate of conversion of energy with respect to time. So it's and moreover, when you read some text related to energy and power, you mainly get confused, right? But as long as you know that, for example, what is the power dissipation in a circuit, how to choose the right resistor for your circuit based on the power dissipation in that circuit, and so on and so forth, for the sake of our discussion right now, it's more than enough. Okay. Now, when it comes to series circuits, basically there are certain things that you need to note. And that is basically that basically, if you suppose that you have 3 resistors over here in a circuit connected to a power supply, right? And this is R1, this is R2, and this is R3, and this is V of S. This you have some, it seems that we are having light problems over here. Okay, so now if you have this circuit here, basically what happens is that you have R1, R2, R3, and you have V of S, and you have some voltage across R1, which you can call V of R1. You have some voltage across R2, which you can call V of R2, and some voltage across R3, you can call that V of R3. There is some current going through this circuit, and so you can basically the power dissipated by each of these resistors you can calculate by basically squaring the current going through the circuit and then multiplying it by each of these resistors. For example, whatever the current here is going through the whole circuit, square it and multiply it by R1, you will get the power dissipation by R1. Square this and multiply it by R2, you will get the power dissipation by R2. Square this current and multiply it by R3, you will get the power dissipation by R3, right? Moreover, you can of course calculate the total resistance in this circuit, because this is a series circuit, and so R of t would be, for example, R1 plus R2 plus R3, right? And then regard that as one resistor, and then use this for example, this formula P is equal to V times I. So you have your voltage and the current, and then you would get some value which would be the power dissipated in this whole resistor here. And what you would find out is that basically if you calculate the power dissipated by this R1 individually and the power dissipated by R2 individually and R3 individually and add them together, that would be the total power dissipated in the whole circuit if you basically regard all of these resistors as just one resistor and calculate the total power dissipation in the whole circuit, right? Which means that the power dissipated in a series circuit is equal to the sum of the basically the power dissipations that occur in each of those resistors. Meaning that, for example, just as in a series circuit, for example, we have the fact that, for example, the voltage across R1 plus the voltage across R2 plus the voltage across R3, this is supposed to be R3, the sum of these voltage drops is equal to the power supply voltage. In the same way, the power dissipation of R1, the power dissipation of R2, the power dissipation of R3, if you add them together, just add them together like this algebraically, you will get the total power dissipation in the circuit. That's basically all that you need to know here. Now, let's do a couple of examples here in order to verify this and just end this video, right? Okay, so now let's solve an example. Okay, so the example that we have is a series circuit consisting of 3 resistors. So you have one resistor here, for example, R1, R2, R3, and let's say that this is R1, this is R2, and this is R3, and this comes over here, positive, negative, and you have this circuit over here, right? So this is V of S. Now in this circuit, R1 is equal to 330 ohm, R2 is equal to 680 ohm, and R3 is equal to 910 ohm. Okay. Now what I want to show you is that the power dissipation, if you calculate the power dissipation individually in each of these resistors in this circuit, that the sum of those individual power dissipations is going to be equal to the total power dissipation in the circuit, right? That's what I want to show you. So for that purpose, we need to calculate the individual power dissipations across these resistors. And so what I'm going to do is that, so for example, to calculate the power dissipation in R1, I can use any of these three formulas. P is equal to V times I, P is equal to basically I squared times R, and P is equal to V squared by R. If I use this, for example, this formula, I will not need the current through the circuit, because I can simply calculate the voltage across these resistors and then square it, multiply it by the value of R, and calculate the voltage across that resistor. Meaning that basically, for example, the voltage across R1 in this side, so V of S over here, of course, is 150 volts, by the way. So the voltage across R1, V of R1 in this circuit is equal to basically R1 divided by R of T in the circuit times V of S. So we need R of T, we need to calculate what the R of T. Now R of T in this circuit is equal to R1 plus R2 plus R3, which is equal to, well, 330 ohms plus 680 ohms plus 910 ohms, which is the same thing as, let me use a calculator. 330 plus 680 plus 910, that's equal to 1920 ohms. So R of T is equal to 1920 ohms, right? So what that means is that then V of R1 would be equal to R1, which is equal to 330 ohms by 1920 ohms times V of S, which is equal to 150 volts. That would be equal to basically 330 divided by 1920 times basically 150. That is equal to 25.8. That is equal to 25.8. 25.8 volts. It's not that much, really. Okay. 25.8 volts. V of R2 would be equal to basically R2 by R of T times V of S. So R2 is equal to 680 ohm over 1920 ohm over times 150 volts, which is the same thing as 680, which is 680 divided by 1920 times 150 volts. That's 53.1. That's 53.1 volts. And V of R3 is the same thing as R3 by R of T times V of S, which is equal to 910 divided by 1920 times 150 volts. These are all in ohms. that is equal to basically 910 divided by 1920 times 150 is equal to 71 volts. There's something wrong here, I suppose. 71.1 volts. And if I add all of these voltages together, 71.1 plus 53.1 plus 25.8, that's exactly 150. There's nothing wrong here actually. Okay, so these are the voltage drops across these resistors. V of R1, V of R2, V of R3. So that means that the power dissipation across each of these resistors would be then basically you can say that P of R1 would be equal to V squared. So V of you could call it basically P of R1, you could call it basically V of R1 divided by V of R1 squared divided by R1, right? Divided by R1, which is equal to, for example, over here 25.8 squared. 25.8 squared divided by R1, and R1 is basically 330 ohms. 330 ohms. P of R2 would be equal to V of R2 squared divided by R2, which would be equal to 53.1 squared divided by 680 ohms. That is voltage squared by ohm. So that would be in watts. That is voltage squared by ohm. That is again voltage squared by ohm. Next we have P of R3. Next we have P of R3 is equal to V of R3 whole square divided by R3. So V of R3 we calculated here to be 71.1 squared divided by R3, which is equal to 910 ohms. This is volts squared. And that is equal to, let me calculate this, 25.8 squared and divide that by 330. That's 2.02 watts. That's 2.02 watts. Now if you calculate 53.1 squared and divide that by 680, you would get 4.15 watts. And 71.1 squared and divide that by 910, you have 5.56 watts, right? That is the power dissipation across by R1, R2 and R3, right? Now the same circuit, the total power dissipation in the circuit, we said that R of T was 1920 ohms. V of S was basically 150 volts. So the current going through the circuit is I is equal to V to R, which is the same thing as 150 volts per 1920 ohms, which is the same thing as 15 by 192, which is 0.0781. 0.0781 amps, which is basically 78.1 milliamps. 78.1 milliamps, right? Now, what that means is that then the power dissipation by this whole circuit would be V times I, which is equal to 150 volts times I, which is 0.0781 amps, and then that would be equal to so 781 amps times 150 volts, that's 11.7 watts. 11.7 watts. That's the total power dissipation by the circuit. Now, if I add all of these together, if I add all of these power dissipations together, you can see that I will have basically 2.002 plus 4.15 plus 5.56, that's 11.73 watts, and that is exactly equal to what we got over here, which basically means that when you have a series circuit like this, the power dissipation in this resistor plus the power dissipation in this resistor plus the power dissipation in this resistor, if you add them together, that becomes the total power dissipation in the whole circuit, which is exactly like, for example, the voltage distribution in a series circuit. Meaning that, for example, in a series circuit, the voltage drop across R1, across R2, and across R3. When you add them together, that becomes the power supply voltage. And again, here, when it comes to power, the power supplied by the power supply is basically equal to the individual power dissipations in each of these resistors added together. That becomes the same amount, right? Okay, now in the next video we will talk basically about power dissipation in parallel circuits. I'll see you in the next video, and thank you.